Alright, the final type of isomerism that we're going to talk about in this class is optical isomerism. And the reason they call it optical isomerism is because when you have something that's optically pure, as they said, or has just one optical isomer in it, it will rotate plane polarized light, which is something that most of the time doesn't really impact organic chemistry that much, but there's some really cool demonstrations of optical effects if you have something that can rotate plane polarized light and polarizing sunglasses and those types of things. We're going to look at just what optical isomerism is and where it comes from in an introductory sense. And this is something that's really important for how different molecules can interact with each other. So whether they interact with light or not isn't so important to the chemist, as is how the molecules interact with each other. So this type of isomerism can occur and often occurs when there are 4 different substituents on a carbon atom. So as you know, when a carbon obeys the octet rule, it generally has 4 things bonded to it. And when those 4 things are different, then you have a chiral carbon, and it's got special properties and can cause optical isomerism. This can get very complicated because sometimes when there's 2 chiral carbons, you can end up overall not having optical isomerism. So rather than going into a full-blown treatment of this, we'll just introduce the most common and straightforward way to have optical isomerism. That's when you have a carbon with 4 different substituents on it. If there's only one such carbon in a molecule, then it will be optically active and will be special because of this. Compounds with optical isomerism can either be identical, so if you have 2 compounds with the same formula that have chiral carbons, they're either going to be identical, and what people say there is they're superimposable. Meaning if you place them on top of each other, they will be verifiably identical. Or they will be mirror images of each other. So if something's got a chiral carbon and is optically active, it will either be identical to another compound or it'll be a mirror image of the other compound. And so I'll give you some examples so you can follow along what I mean. Mirror images of optically active compounds are called enantiomers and are different. So where this comes from is I go ahead and build a molecule with a chiral carbon, and I like a really simple one. Simple examples are often best to illustrate things for beginners or for a first example. And so 1-chloro, 1-ethanol, 1-chloro, 1-ethanol. So for 1-chloro, 1-ethanol, you have 2 carbons. On the first carbon is the alcohol group, so it makes OH. And then you also have a chlorine on the first carbon. That means there's 1 hydrogen on the first carbon. And then the second carbon, filling out the octet rule, has 3 hydrogens on it. So here's a nice picture of 1-chloro, 1-ethanol. And the first carbon here is chiral because it has 4 different groups on it. It has an OH, a hydrogen, a methyl, and a chlorine. So 4 different things on that carbon makes this chiral and is optically active. This drawing does not have chirality because it's planar. But if I were to build this molecule, ta-da, and this I consider to be my mascot for chirality and optical isomerism. It looks like a cute little doggy. Bark, bark. And this guy, now you can see the OH group, the hydrogen, the chlorine, and the methyl. And this one is a certain isomer, right? If I go and just sort of randomly build another one of these, then it's either going to be identical to this one, meaning exactly the same, And that's where they say superimposable, because these two are identical. And if I say, are these superimposable, I'll try to place them one on top of each other and verify that everything lines up and is in the same position. So there's a hydrogen in the same place as a hydrogen, an oxygen in the same place with an oxygen, carbon in the same place with a carbon, chlorine in the same place with a chlorine. These two optically active compounds, one chloro, one ethanol, are exactly the same. So these are identical and superimposable, whereas these two are mirror images of each other. So if you take a look at this, and I'll actually put this one on this side so I can overlay it with a picture that looks similar in terms of orientation, is a mirror image for this one. If you envision a mirror here, what's far away from a mirror reflects and looks like it's far away. So the chlorine is reflecting with the chlorine, hydrogen's reflecting with the hydrogen, hydrogen's reflecting with the hydrogen, methyl's reflecting with the methyl. These two are essentially perfect mirror images. And when I try to superimpose them then, when I line up the heads with the tails, right, these guys are lining up, the OH group and the methyl, but now one of the chlorines is on the left and the other one's on the right. So those are not superimposable. When I try to superimpose them, I see that they're different. So these two mirror images of chiral molecules are not superimposable and are actually different compounds. I can try another strategy and try to line up the chlorine and the hydrogen. Again, this one's a little more difficult because of the management of the other groups, but there we go. We've got the hydrogen and the chlorine lined up. Now you can see the head's lining up with the tail. It's not working out. So these two are clearly different. I cannot superimpose them and have everything line up. They are mirror images. So if I wanted to draw a mirror image of this guy, I would just reflect across like such. Again, the two-dimensional molecules are not chiral. You need to have this three-dimensionality. But there's me drawing the mirror image of a chiral molecule and showing its picture. So hopefully you can see that if you have a carbon with 4 different groups on it, it's special, it's chiral, and if you built a chiral molecule, you'd either get what you might call the left-handed version, where this one, my doggy's left hand is green and it's the chlorine, or you get the right-handed version. And those two varieties are two distinct compounds with different interactions with other chiral molecules.